Bismillah ar-Rahman ar-Rahim. Dear students, my dear students, dear followers, here we are at National Higher School of Mathematics, Algiers. I am Professor Muammar bin Bashir from National Higher School of Mathematics, and today's video will deal with sequences. Here we have a theorem. So this theorem says that if we have, let un and vn be two real sequences, we suppose that un converge to a when n goes to plus infinity, and vn converges to b when n goes to plus infinity. Then we have 1 for c, a constant c from R. We have cun, this converges to ca. The second result, we have un plus minus vn, this converges to a plus minus b. And the third result, we have un vn converge to a b. The fourth result, if we suppose that b is different and of 0, then we have 1 over vn converge to 1 over b when n goes to plus infinity in good conditions. And fourth, we have un over vn, the same condition, we suppose that b is different of 0. This converges to a over b. Let us move to the proof. So here we need the first point and the second point. First point and the second point are trivial. We need just to write. For the third point, we consider, so we say that un vn converges to ab. We say that un vn converges to ab. This is equivalent to the characterization, the following characterization: for all epsilon greater than 0, there exists a rank which depends on epsilon from n, such that for all n greater than or equal to n of epsilon 0, we have the difference between un and vn, between un vn and ab, this is less than or equal to epsilon. So we need to prove this one, we need to prove this characterization. We have that un converges to a. This is equivalent to say that for all epsilon greater than 0, there exists a rank n1 of epsilon from n. such that for all n greater than or equal to n1 of epsilon, this implies that the difference between un minus I is less than or equal to epsilon. And we have Vn, which converges to B. This is equivalent to the characterization for all epsilon greater than 0. There exists a rank n index 2 which depends on epsilon from n, such that for all n greater than or equal to n2 of epsilon, this implies that the difference Vn, the difference Vn minus B is less than or equal to epsilon. So, to be able to say that un Vn converges to AB, we need to find n0 such that this characterization is true. So, let us consider un Vn minus un B plus un B minus AB. Here, what we have? Here, we add a term and then we take it off. Using a triangle inequality, this is less than or equal the absolute value of un Vn minus un B plus the absolute value of un B minus AB, which is less than or equal un as a factor, un, absolute value of un, Vn minus B, plus absolute value of B, the difference un minus A. And here we have all the right to put here a capital M times V minus B plus absolute value of B times un minus A. Why do we get this capital M? Don't forget that un is a convergent sequence, and since it is a convergent sequence, this means that it is bounded, and the capital M is an upper bound, the bound of the absolute value of un. And here, what we have from this side, we know that since un converges to A, so there exists a rank n1 of epsilon, and since Vn converges to B, there exists n2 greater than epsilon. From here, we can say that for all epsilon greater than 0, there exists a rank n0 of epsilon, which is equal to the maximum between n1 of epsilon and n2 of epsilon, such that for all n greater than or equal to n epsilon of 0, this implies that the absolute value of un Vn minus AB is less than or equal to epsilon. And this epsilon actually is capital M epsilon plus the absolute value of B epsilon. Since epsilon is any given positive number, so we can consider all this term as epsilon. Even if you don't love this kind of formula, you can here replace. And take in this place which related to V minus B to V minus B. So we take epsilon over capital M over 2, and here we take epsilon over 2 absolute value of b, and the result will be well done. This is about the proof of the third point. How about the proof of the fourth point? For the fourth point, we suppose that Vn converges to b when n goes to plus infinity with b different of 0. Can we prove that 1 over Vn converges to 1 over b? Here, actually, honestly, we need a tricky idea that will permit us to conclude. This idea is as follows. We know that Vn converges to b. This is equivalent for all epsilon greater than 0. There exists a rank n0 of epsilon from n sure, such that for all n greater than or equal to n0 of epsilon, we have absolute value of Vn minus b. This is less than or equal to epsilon. Well, remark that here for all epsilon greater than 0, there exists a rank such that if we consider epsilon, special choose, this is not the unique choose, but this is one among others. If we take this special one, epsilon is equal to the absolute value of b over 2. This epsilon is greater than 0. Since it is greater than 0, this means that there exists n0 of absolute value of b over 2 such that for n greater than or equal n0 of special epsilon, this implies that the absolute value of Vn minus b is less than or equal the absolute value of b over 2. For this special case, we have a rank. Let us concentrate on this last formula. This formula, one has the inverse triangle inequality, implies that the absolute value of Vn minus the absolute value of b, this is less than or equal the absolute value of Vn, which is less than the absolute value of b over 2. All what we did here, we have this double inverse triangle inequality. We use this one. From what, if we compare this part with this part, we will deduce that the absolute value of Vn minus the absolute value of b is less than or equal the absolute value of b over 2, and it is a greater than or equal minus absolute value of b over 2. We have this formula. And here we will just concentrate on this inequality. From this inequality, red color, we deduce that the absolute value of Vn, this one, is greater than or equal. If we take this one to this side, we get plus, so we have plus absolute value of b minus absolute value of b over 2. So this is greater than this formula. This is a very nice formula which wanna help us to achieve the proof. So we are dealing with this formula or property, so I can use this place. So we are here. Don't forget this. And let us consider 1 over Vn minus 1 over B. This is less than or equal absolute value of B minus Vn over Vn B, which is the same, so this is equal, which is less than or equal the absolute value of Vn minus B over the absolute value of Vn times the absolute value of B. We are here. But here we have the absolute value of Vn is greater than equal the absolute value of B over 2, which implies that 1 over the absolute value of Vn is less than or equal to the absolute value of B. So we will use this trick here, which is less than or equal to the absolute value of B squared times Vn minus B. But don't forget that Vn converges to B. Vn converges to B. This means that there exists a rank n0 such that this is true. What we can, as a summary, for all epsilon greater than 0, there exists a rank n1 of epsilon, which is the maximum between n0 of epsilon, and this concerns the general case, and this is the special case. We take both informations to deduce such that for all n greater than or equal to n1 of epsilon, one has the absolute value of 1 over Vn minus 1 over n is less than or equal to this one, B squared, and here we have epsilon. Since epsilon is any given one, so we can consider that this is epsilon. Even if we don't like this kind of forms, we can just make a change here. So this ends the fourth point. And the most important idea in this proof is about this boundedness. Let us move to the last point of this theorem, which is quite simple. Why this is simple? This is simple because to prove the fifth property, we use the fourth and the third properties together. So here we consider un over Vn. This is equal un times 1 over Vn, and this goes to A over B. Why? Because here we use the third property. The third property says that if we have the product, so the product of un Vn goes to the product of the limits. From the fourth property, we know that 1 over Vn goes to 1 over B, and we get this result. This finish the proof of this theorem. Next, let us move to sequences which tend to infinity. We have definition or characterization. The limit of un is equal to plus infinity when n goes to plus infinity. This is equivalent to the following characterization. For all A positive, there exists a rank such that for all n greater than or equal this rank, natural number for sure, this is in n, which implies that un is greater than A. As an example, Let us consider un equal a power n, and a is strictly greater than 1. Show that un goes to plus infinity, 1n goes to plus infinity by using this characterization. How we can solve this example? So using the characterization, we can try to show the existence of the rank n of a, which depends on a. So let a be real number, positive real number, and consider un greater than a or equal. This means that we are trying to find the rank. This is the most important. So here we have an greater or equal a, which is equivalent to, we take ln, and since ln is an increasing function, so we get n ln a, which is positive, and this is greater than or equal to ln a, which is equivalent to n greater than or equal to ln capital A over ln little a. So we can consider n of a as the integer part of ln capital A over ln a plus 1, and the characterization will be satisfied. We say that a real sequence un goes to minus infinity, 1n goes to plus infinity. This is equivalent. Actually, we can retrace the same definition. For all a greater than 0, there exists a rank n of a, such that for all n greater than or equal to n of a, this implies that un isn't greater than or equal to a, but this is less than or equal to minus a. Very, very easy. Monotone sequences definition. Let un be a real sequence. So un is said to be non-increasing if un plus 1 is less than or equal to un for all n in n, or a part of n. un is said to be a non-decreasing sequence, a non-decreasing sequence if un plus 1 is greater than or equal un for all n in n. Actually, better we can write if for all n in n, un plus 1 non-decreasing greater than or equal to n, and here if for all n in n, un plus 1 is less than or equal un. This is the first definition. The second definition, the third definition, un is said to be decreasing if for all n in n, un plus 1 is less than strictly than un, so without equal. And the last one, un is said to be increasing if for all n in n, un plus 1 is greater than un. The sequence un is said to be monotone, or sometimes we say monotonic, monotonic, if it is non-increasing, neither, or if it is neither non-increasing, if it is neither monotonic, if it is either non-increasing or non-decreasing. The sequence un is said to be strictly monotonic, monotone or monotonic, if it is either increasing or decreasing. Criteria or monotonicity check, remark. We can check the monotonicity of a sequence by using un plus 1 minus un, the difference, or we can use un plus 1 over un, and we have to compare it with 1. Here we compare the difference with 0. If this is greater than or equal 0, we say that un is non-decreasing. If it is strictly greater than 0, we say that un is increasing. If it is less than or equal 0, we say that it is non-increasing. If it is strictly less than 0, we say that it is decreasing. Here, if it is strictly greater than 1, if it is greater than or equal 1, we say that it is non-decreasing. If it is less than or equal 1, we say that it is non-increasing. If it is strictly greater than 1, we say that it is increasing. If it is strictly less than 1, we say that that is decreasing. If it is equal to 1, we say that it is a stationary, constant sequence. If it is equal here to 0, we say that is a constant sequence. What do we have next? We have an example. For example, we can take this sequence un minus 1 over n, and to try to un equal 1 over n. And to try, we have 1,000 different methods. We have a very nice theorem. This theorem says that all bounded monotone sequences converge. All bounded monotone sequences are convergent. So if we take a monotonic sequence, it must be unbounded, it must be convergent. So let un prove without loss of generality. We can suppose that un is non-increasing. It is non-decreasing. It is non-decreasing. This means what? This means that for all n in n, or a part of n, it is non-decreasing. This means that un plus 1 is greater than or equal to un. Since it is non-decreasing, so it is lower bounded. Necessarily it is lower bounded, but this is not sufficient. For example, if we take the sequence un equal n, it is lower bounded, but it goes to plus infinity. When we say that it's bounded, we mean the other born. So it is naturally, since it is non-decreasing, so it is naturally lower bounded, and this hypothesis means that it is upper bounded. So it is bounded. Let us consider this set un and in n or a part of n. Since we suppose that un is bounded, this means un is bounded. This means that there exists a constant m from R, or a positive one. Let us say that a positive one, such that what? Such that for all n in n, we have un less than or equal to n. Here, S is bounded too. It is upper and lower bounded. We need just to know if it is upper bounded. And since this is the hypothesis that this is upper bounded, we can say, thanks to completeness axiom or theorem, that sup of S is equal exist. So a set from R which is upper bounded admits a supremum. So sup of S exists, and more than just sup of S exists, we suppose that sup of S is equal to U. We show that limit of un is equal to the sup of S and equal to u1 and goes to plus infinity. Sup of S which is equal to u, this is a supremum. Since this is a supremum, we have characterization of supremum. We will use the characterization to conclude that the sequence converges to U starting from a rank. We have the difference less than or equal to epsilon. Sup of S equal U. This is equivalent 1 and 2. For all un from S, we have un less than or equal to U, the characterization, and for all epsilon greater than, there exists an element U capital N, so there exists a rank N such that U capital N from S verifies what this verifies. This verifies U minus epsilon strictly less than U capital N, which is less than or equal U, which is the supremum. But here, don't forget that the important thing that our sequence UN is non-decreasing. Since it is non-decreasing, this means that we have UN plus 1 greater than or equal to UN. What we can deduce? We can deduce that for all epsilon greater than 0, this is a fact, so UN exists, and this formula is true. For all epsilon greater than 0, there exists a rank n0 of epsilon which can be taken as this n, such that for all n greater than or equal to n, this implies that what we have u minus epsilon. This is due to the characterization, which is less than un. This is due to the characterization, but this is less than or equal to un. Why? Since n is greater than or equal to capital N, this one, this means that un is greater than or equal to u capital N. Why? Because our sequence is a non-decreasing one, but un is an element from S, so this verifies this inequality. And since this is less than or equal u, this is less than or equal to u, large estimation, plus epsilon, the same epsilon. From what? If we compare these three terms, we deduce that for all epsilon greater than 0, there exists a rank n0 of epsilon which is related to n, such that for all n greater than or equal to n0 of epsilon, this implies, if we compare these three, this means that un minus u is greater than minus epsilon and less than or equal to epsilon. This means that un minus u is less than or equal to epsilon, which finishes this proof. Very nice definition. The next paragraph will concern adjacent sequences, and honestly speaking, adjacent sequences we can find definition in English books, but these terms, this terminology, this convention doesn't exist as far as I know in English. Actually, it is our definition that we put it according to French and Arabic programs. We can find these words, but in English, I repeat, these words, as far as I know, doesn't exist. But the definition, the mathematical consideration, we can find this in English, just the terms that we cannot find. So, definition. Adjacent sequences. Definition. We say let un and vn be two real sequences we say that un and vn are adjacent if one is non-increasing, the second is non-decreasing, and the difference Vn, for example, minus un tends goes to 0 when n goes to infinity. This is the definition. In other terms, for example, we can consider Vn such that for all n in n, Vn plus 1 is greater than or equal Vn. Un is such that for all n in n, un plus 1 is less than or equal to un. And the limit of Vn minus un equals 0 when n goes to plus infinity. This is the definition of two adjacent sequences. For example, very easy example, we can take un equal 1 plus 1 over n and Vn equal 1 minus 1 over n. One is non-decreasing. This one is actually increasing, and this one is decreasing. They tend to the difference between them goes to 0. This means that by the definition, this means that they are adjacent. Here we have a very nice proposition. This proposition says. Let un and Vn be two adjacent sequences. Then, when they are they are convergent. This is the first point. And the second point, they converge to the same limit. Very nice. So it is sufficient to show that we have two sequences which are adjacent, and this is enough to say that they are convergent and they converge to the same limit. If the questions asked us to find the limit, in this case we need to find the limit. So, without loss of generality, proof. Without loss of generality, we can suppose that Vn is non-decreasing. It is non-decreasing. And Un is non-increasing. Okay, we suppose that it is non-increasing. We suppose that Vn minus Un goes to 0, 1n goes to plus infinity. And let us consider Wn, which is equal to Vn minus Un. We need to check if Wn is increasing or decreasing. To this end, we consider Wn plus 1 minus Wn. I forget to say that when we use the difference between sequences to check the monotonicity, if the sequence is presented as a sum, so the formula is an additive. But if it is multiplicative, we use the criteria Wn plus 1 over Wn. So if we have to compare to 1, this means that we are dealing with a multiplicative kind of sequences. If we use the difference and we compare to 0, this means that we have a summative and additive sequence. Let us consider this one, and here what we can get, we can get that Vn plus 1 minus Un plus 1 minus Vn minus Un. This is equal to Vn plus 1 minus Vn minus Un plus 1 minus Un. You check this is true. What we suppose? We suppose that Vn is non-decreasing. If it is non-decreasing, this means that this is negative. Non-decreasing, non-decreasing, non-increasing, non-decreasing. This means that Vn plus 1 is greater than or equal to Vn. So this is positive or equal to 0. And Un is non-increasing. Un is non-increasing. This means that Un plus 1 is less than or equal to Un. This means that this is negative times by minus 1. This means all this one is greater than or equal to 0. I repeat once again. Vn is non-decreasing. This means this one. And if this is true, this means that this is positive. And Un is non-increasing. This means that this case. And if this is true, this means that this is negative from this formula. And with times by minus 1, we can remark that this is positive and this is positive, which means greater than or equal to 0. Here what we have? We have Wn, this is the new sequence. This function, it is increasing. So this function is non-decreasing. So it is non-decreasing. And by hypothesis, this goes to 0. Goes to 0. It is non-decreasing and it goes to 0. This means what? This means what? This means that so it goes to 0. So it goes to 0 and it is non-decreasing. This means that it grows up. This means that it goes to 0 like this. This is formula, I don't know, but it comes from lower and it goes to 0 since it is non-decreasing. This means what? This can be translated. This can be translated by. This can be translated by the following: a tricky and basic idea. This means that Wn is less than or equal to 0, which implies that Vn is less than or equal to Vn. And let us back to our hypothesis. We suppose that Vn is non-decreasing. Vn is non-decreasing. This means that Vn plus 1 is greater than or equal. Vn is non-decreasing, is greater than or equal to Vn. And Un is non-increasing. This means that we have Un plus 1 is less than or equal to n. In this place, we have Vn less than or equal to Un. And Un is such that this one. So we can permit to ourselves to write U0. And I will keep the same formula. Vn less than or equal. And Vn is greater than or equal to Vn. This means that we have all this V0. I will put it here. So we have Vn less than or equal to Un, which is less than or equal to U0. This is one. And in the another sense, we have Vn less than or equal to Un, which is greater than V0, the first one. So, the first point that shows that this is convergent, from this sense, we have Vn which is non-decreasing and it is upper bounded. So it is convergent. And Un, it is non-increasing and it is lower bounded. So it is convergent. And this permits us to deduce and to prove that both sequences are actually bounded. Here we need to show that they converge to the same limit. First, we proved that they are convergent. And secondly, if they are convergent, this means that the first converge to, for example, Un converge to A and Vn converge to B. And since the difference between them converge to 0, this means that the limit converge to A minus B or B minus A. And since this is equal to 0, this means that A is actually equal to B. This finish this session. The next session will be about subsequences. I hope that it wasn't very long. Hope this video will be helpful. Dear students, dear followers, thank you very much. See you next time, inshallah.